So the last speaker of the day is going to be Andrea Cappelletti, and the title of his talk is Protoadditive Functors and Pretorsion Theories in a Multipointed Context. Andrea, you can start whenever you want.
Thank you, Ivan. Good afternoon, everyone. I am Andrea Cappelletti, as Ivan said, and I am an almost former PhD student from Università degli Studi di Milano. And today I want to present a joint work with Andrea Montoli, my PhD supervisor. So let me introduce briefly the idea behind this work. In my PhD thesis, I've studied a non-pointed version of the notion of torsion theory in the category of many-valued algebras. And so the nice results obtained in this setting, served as a starting point in order to provide a sort of generalization to a multi-pointed context of some known results for the pointed setting about the connection between torsion theories, Galois structures, and factorization systems. So let's start by introducing our framework. I'm having a problem with the presentation because, okay, sorry. So we assume to work in a bar exact and protomodular category C with finite coproducts. And as you can see, this category, such a category, is almost a semi-abelian category. It fails only to have a zero object. And therefore, we define the class of zero objects as the full repeat subcategory of C, determined by the initial object 2 and the terminal object 1. And here I'm using this notation for the initial object because of our starting example, because, you know, in the category of M algebras, or if you want, in the category of Boolean algebras, usually the initial object is not 2. Moreover, we say that morphism of C is trivial if it factors through an object of the class Z, that is the class of zero objects. In addition, we require that the initial object 2 is different from the terminal object 1 in order to exclude the non-pointed case. We require that every universal arrow from the initial object to a non-terminal object is a monomorphism, which is a trivial condition in the pointed situation, but in this case we have to require it. And finally, we want that the terminal object is strict, meaning that if we have an arrow with domain isomorphic to the terminal object, that also the codomain must be isomorphic to the terminal object. And this formalizes, in a sense, our idea of a multi-pointed context, because, you know, if you consider, for example, the situation of Boolean algebras or rings with unit, then if you take an arrow with domain the algebra 0 equal to 1, then you must have that 0 is equal to 1 also in the codomain, and then the codomain must be the terminal object. So Boolean algebras, I-think algebras, and M algebras are examples of this situation of the category satisfying our assumptions, and also the dual of the category of set is an example of a category satisfying our requirement. More generally, we have that for every elementary topos E, it is equivalent to require that E is a two-valued topos, and that the condition B, condition 2 of this slide, falls in the dual of the elementary topos. And so we get that every category of the form dual of a two-valued elementary topos is a category satisfying our conditions. So there is a notion of kernel for a non-pointed setting, that is the notion of Z prekernel, or simply prekernel, because in our setting we are fixing our class of zero objects. So given an arrow F of our category C, we say that K is a prekernel of F if the composition between F and K is a trivial morphism, and the K is universal with respect to this property, as in the usual situation for kernels. And then we get a nice description of per kernel in our setting, since if we consider an arrow with no terminal codomain, then the per-kernel of this arrow is given by the pullback of the arrow along the universal morphism from the initial object to the codomain. And if the codomain of our arrow is the terminal object, then the per-kernel is given by the identity of the domain. And so in our setting, per-kernel always exists. Dualizing this notion, we get the definition of Z per-kernel or Preco-kernel. And here we have a very difference between the pointed case and our multi-pointed setting, since in our situation, nothing ensures the existence of Preco-kernels. For example, if we suppose that the product between the initial object and itself is not isomorphic to the initial object, then the identity on this product does not admit a Preco-kernel. But if the Preco-kernel of an arrow F exists, then it is given by a push out of this form, where Q is the Preco-kernel of F, and Z is a zero object, so an object of our class of zero objects, depending on F. The notions of per-kernels and Preco-kernels naturally lead to the definition of a short Z per-exact sequence, or simply short per-exact sequence, which is a diagram of this form where F is the per-kernel of G and G is the Preco-kernel of F. And so this definition is a fundamental tool in order to introduce the notion of Pretorsion theory. The idea of Pretorsion theory is a generalization of the concept of torsion theory to a non-pointed setting, which is in turn a generalization of the situation given by the inclusions of the torsion abelian groups and the torsion-free abelian groups in the category of abelian groups. Formally, a Pretorsion theory on a category C is given by full repeats of categories of C, let's say T for torsion and F for torsion-free, such that every morphism from a torsion object to a torsion-free one is a trivial morphism, and for every object A, we have a pre-exact sequence of this form where T of A is a torsion object. Let's say it is the torsion part of A, and F of A is a torsion-free object, and it is the torsion-free part of A. It can be proved that such a sequence, given an object A, is unique up to isomorphisms, and so fixing for every object A such a sequence, we can define two functors, the functor F from C to the subcategory F, and the functor T from C to the subcategory T, where the functor F associates to each object torsion-free part of that object, and the functor T associates to each object the torsion part of that object. And it can be proved that F is always a left adjoint of the inclusion of the category F in C, and T is a right adjoint of the inclusion of the category T in C. Theories, Galois structures, and factorization systems in this multi-pointed context. And so I have to recall the definition of Galois structure. Janelids proved that the Galois correspondence theorem can be extended to a categorical setting if we work with admissible Galois structure. And so you can think about a Galois structure as a generalization of the notion of Galois connection with classes of arrows, I mean. And formally, a Galois structure is given by an adjunction between a functor S and a functor C into admissible classes of arrows A and B, where we say that a class of arrows is admissible when it contains all the isomorphisms, it is closed under pullback and under composition. And so in order to have a Galois abstraction, we require that S of A is contained in P, C of P is contained in A, and moreover, every unit of this adjunction is an arrow of A, and every component of the unit of this adjunction is an arrow of A, and every component of the co-unit of this adjunction is an arrow of P. So such a structure allows to define for every object A two functors, SA and CA, where SA is given by S on arrows, and CA is given by the pullback along the unit of this adjunction. And we have that the functor SA is always the left adjoint of the functor CA for every object A. And so we say that Galois structure is admissible whenever the functor CA is fully faithful for every object A. So Galois structures are a useful tool in order to classify arrows of the class A. And here in this definition, I am making a little abuse, but never mind, because this definition is good enough for our purposes. Okay, so we say that an arrow F of A is a trivial extension if the diagram given by the commutative, given by the mutative diagram given by the naturality of the unit of the adjunction is a pullback. We say that F is a normal extension if it is a regular epimorphism, and in fact here I would have put the notion of effective descent morphism. I don't have time. So if it is a regular epimorphism and its kernel pair projections are trivial extensions. And then finally, we say that an arrow F is a central extension if there is a regular epimorphism such that the pullback of F along this regular epimorphism is a trivial extension. And the terminology behind this definition is justified by the situation of the reflection of the William groups in the category of groups. In fact, if we consider such an adjunction as a Galois structure with classes of arrows, the classes of surjective group homomorphisms, we get that this categorical notion of the central extensions coincides with the classical one for group theory. And finally, I would like to recall the definition of a factorization system. So factorization system is given by a pair of classes of arrows in a ODC, let's say E and M, such that for every square of this form where the top horizontal arrow is an arrow of E and the bottom horizontal arrow is an arrow of M, then there is a unique diagonal making the two triangles commute. And moreover, we require that every arrow of C, factors as the composition between an arrow of M and an arrow of E. We say that the factorization system is stable if the class E is pullback stable, and this means that our factorization is stable under pullbacks. And so we are ready to investigate this connection between Pretorsion theories, Galois abstraction, factorization systems in our multipointed context, and this part of the work was strongly inspired by the very nice results obtained in this paper by Everard and Gran. And in this work, they provided a definition of a protoadditive functor in the context of the semi-abelian categories. They say that a functor is protoadditive if it preserves split short exact sequences. And moreover, they provided a characterization for this property. They proved that a functor is protoadditive if and only if it preserves the zero object and the pullback along split epimorphisms. And so this characterization allows to a generalization to our setting of this notion. And we say, in fact, that a functor F is protoadditive if it preserves the terminal object, the initial object, and the pullback along split epimorphism. And so, as in the original work, we say that a Pretorsion theory satisfies condition P if the reflector is protoadditive. And moreover, we introduce, again, as the original work, the condition N is a condition of normality for our Pretorsion theory. And we say that a Pretorsion theory satisfies condition N if for every diagram of this form, where K is the prekernel of F and TKF is the torsion part of KF, then the inclusion of this torsion part in A is the prekernel of some arrow. And here we have another big difference from the pointed case to our multi-pointed setting. In fact, in the pointed case, given a torsion theory, we have that an object T is a torsion object if and only if f of t is equal to 0. In this case, we have two possibilities. In fact, we have torsion objects such that f of t is equal to 1, and torsion objects such that f of t is equal to the initial object. And so, in order to guarantee our results, we have to require some conditions about the class of torsion objects that are mapped to the terminal object by the reflector F. And so we say that our pretorsion theory satisfies condition C1 if f of t equal to the terminal object implies that the torsion part of the object given by the product between T and a general object K is isomorphic to the torsion part, the torsion-free part, sorry, of A. And so this is a condition about the behavior of these objects with respect to the torsion-free part of our torsion theory. And the other side of the topic is condition 2. And this is about the behavior of the torsion part of our pretorsion theory. And we say that the pretorsion theory satisfies condition C2 if f of t equal to 1 implies that this sequence is pre-exact for every non-terminal object A. And moreover, we require that the product between the initial object and our object T is again a torsion object. Now we are ready to state our first result about this multi-pointed setting that is, to be honest, a very simple variation of one of the results provided in the paper that I introduced before. And so we have that pretorsion theories satisfying condition C1 corresponds to precokernel reflective subcategory F of C, such that the reflector preserves the terminal object, and this adjunction, seen as a Galois structure, is admissible with respect to the class of all arrows. And here, this precokernel stands for this property. We are saying that every component of the unit given by this reflection is a precokernel in our sense. And the idea behind this fact is quite simple. If we consider such subcategory, we can prove that this is the torsion-free part of torsion theory, constructing the torsion part, taking all the prekernels of the component, of all the components of the adjunction of this reflection. Moreover, if the pretorsion theory satisfies condition P, we can characterize central extensions in a nice way. And again, this is a generalization of a result provided in the original paper. And then we have that a regular epimorphism F is a normal extension for the induced Galois structure, if and only if it is a central extension, if and only if it has a torsion-free prekernel. And the other side is given by this correspondence. We have proved that pretorsion theory is satisfying our condition of normality N, and the condition C2 about the behavior of torsion objects with respect to the torsion part. So we have this correspondence between these pretorsion theories and a stable factorization system EM, such that every arrow of E is a precokernel, and the universal arrow from the initial object to the terminal object is an arrow of M. And again, the idea is not difficult. So we can start from pretorsion theory, and then we can construct E as the collection of the precokernels with a torsion prekernel, and M as the collection of arrows with torsion-free prekernel. And here we have to use this condition in order to get our factorization, because we want to compute a quotient and compute this quotient thanks to this property. And on the other side, the other end, given a factorization system, we can define our Pretorsion theory taking T as the full subcategory of C, whose objects are the object T, such that there is an arrow into a zero object. So it can be 2 or 1, and such that this arrow belongs to the class E. And F is defined as the collection of objects such that the universal arrow into terminal object is an arrow of M. And now I would like to present some applications and some examples about these results. Let's start with our guiding situation, the category of M algebras. You can think about an M algebra as a non-idempotent generalization of the notion of Boolean algebra, or if you want, as a commutative noid with a binary operation that satisfies these axioms. And so, given an M algebra, it is always possible to define a natural order on this M algebra, And so we say that an empty subset of an M algebra is an ideal if it is closed under minorance and under some elements of the subset. A maximal ideal is a maximal element in the poset of ideals, and we can define the radical of our M algebra as the intersection between all the maximal ideals. We say that an M algebra is semi-simple if its radical is trivial. And so, thanks to this quotient, we can prove that the category of semi-simple M algebras, the full subcategory of semi-simple M algebras, is reflected in the category of M algebras. And then this reflection defines a Pretorsion theory where the torsion-free part is given by semi-simple M algebras, and the torsion part is given by the so-called perfect M algebras. And we say that an M algebra is perfect if it can be written as the union between its radical and the negation of its radical, where the negation of the radical is the collection of all the negations of the element of the radical of A. And then we get this Pretorsion theory satisfies all our conditions. And so we can describe our factorization system, in particular, given a general arrow F between M algebras, we have that this arrow F factors as the composition between an arrow E that is a quotient with a perfect prekernel and an arrow M induced by the universal property of this quotient with a semi-simple prekernel. And moreover, we have that regular epimorphism between M algebras is a central extension with respect to this structure, a structure induced by this Pretorsion theory, if and only if its kernel is a semi-simple M algebra. And here you can see a description of the prekernel of an M algebra that is given by the union between the pre-image of the zero and the negation of the pre-image of the zero. Another example is given by the so-called double negation in Ising algebras. We know that given an Ising algebra H, an element X is a regular element if the double negation of X is equal to X. And we know that we can provide compatible structure of Boolean algebras on the set of regular elements of H. And this construction determines a reflection of the category of Boolean algebras in the category of Ising algebras. And so we have, thanks to this reflection, a Pretorsion theory where the torsion free part is given by Boolean algebras, and the torsion part of this Pretorsion theory in the category of I think algebras is given by the so-called pseudo-deterministic I think algebras, where we say that an I think algebra is a pseudo-deterministic if for every element x, the negation of x is either 1 or 0. Again, this Pretorsion theory satisfies all our conditions, and so we have factorization system this form, and we can prove so that every arrow between I think algebras factors has the composition between a quotient with a pseudo-deterministic prekernel and an arrow with Boolean prekernel. If you want, the quotient is given by this equality and this definition. And moreover, we have that as in the previous case, we have a description for central extension with respect to the structure used by the reflection of Boolean algebras, and we know that a regular epimorphism is a central extension if and only if it has a Boolean prekernel. And finally, to conclude, I would like to present an example in an elementary topos. So we consider the category of M sets. And we know that this elementary topos has two truth values, so it's a two-value topos. And so for every object x of this category, we can define the set fix of x as the collection of the elements of x that are fixed by the action of the monoid M. And this provides the definition of two full subcategories of M set. The first is given by the M set with a trivial action of the monoid M, meaning that x is equal to fix of x. And the second one is given by the M set such that the number of fixed points is at most 1. And we have that this pair of full subcategories is a Pretorsion theory in M set op, the dual of M set, and this Pretorsion theory satisfies all our functions. And so again, we can describe our factorization system and our central extensions. And in this case, I will provide a description in M set. So we have a situation that is in a sense the dual of the ones seen before. And so in this case, M set, again, E is given by the arrows such that the quotient of the codomain of the arrow on the image of the arrow has at most 1 fixed point. And M is given by the arrows such that the quotient of the codomain of the arrow on the image of the arrow is a torsion-free object, meaning that the action of the monoid is trivial. And here you can see the factorization of a general arrow F. And then we get that a monomorphism between two M set is a central extension for the induced structure by this Pretorsion theory, if and only if, let's say, the domain is X and the codomain is Y, if and only if the codomain can be written as the union between the collection of the fixed point of Y and the image of X through the arrow F. So this was my last example. Thank you for your attention. Here you can see the bibliography. Thank you very much.
Thank you, Andrea, for your nice talk. We have a round of applause, and now maybe someone wants to ask a question. Please unmute yourself and ask.
Sorry.
Did someone speak?
I cannot hear.
Okay. Sure. So there is one question by Marino.
Okay.
Yes, good afternoon, everyone. Very nice talk and very interesting results.
Thank you, Marino. Your results are very interesting. I mean, because it's a little generalization of your work.
So
thank you for your mathematics.
No, thank you. But just one question. Do you have monotone light factorization systems among these examples that you mentioned? This is one question. And the other one is the reflection from Heyting algebras to Boolean algebras. Does that gives a non-trivial Galois theory? So these are the two questions.
About the first question, I have to study this, so I have to explore this idea. So I cannot answer at the moment, but I would like to explore this situation. About the other question, since this functor preserves all the pullbacks, I think that the induced Galois structure there is a trivial situation, because it is a very good functor, this reflection, this reflector in the category of Boolean algebras.
Oh, thank you. Just one more remark, not question.
Okay.
When Thomas and I first introduced proto-additive functors, we defined them as functors between protomodular categories.
Okay, sorry.
That preserve split pullbacks along split epis with no conditions about initial and final object. So it was a different. And then in the pointed case, it corresponds to the fact that they preserve split short exact sequences.
Okay.
So you don't need to ask anything about the 0 and 1.
Okay.
Or 2 and 1 in your
sorry about the mistake about the reference. Sorry.
Curiosity.
Thank you again, Marino.
Thank you, Marino. Do we have other questions? Okay, seems that we don't. So we thank Andrea for the nice talk. And I think for today we have finished. I would like to thank everybody for joining, especially the speakers, Enrico, Andrea, and Julia. And if people want to hang here, then people can stay. But everyone that wants to leave is allowed to leave now. So I will stop recording now. Oh, and see you in September for the next event. Now we have the break for the summer.